Hello, I am Jinhyeok Kim from ADAS Lab, Seoul National University. Today I'll present SparseLoRA, accelerating LLM fine-tuning with contextual sparsity. This paper is accepted in ICML 2025 poster. As you can see in this title, this work targets compute efficiency during PEFT, not just memory savings, by exploiting a phenomenon called contextual sparsity. Before we deep dive into the paper, let's quickly learn about some backgrounds such as LLM architecture, PEFT, contextual sparsity. First, let's quickly recap the architecture of modern large language models. Most state-of-the-art LLMs, such as GPT, Llama, Gemma, QN, adopt a decoder-only transformer architecture. Each transformer layer consists of two main soft layers. The first soft layer is the multi-head self-attention module. It contains four linear projections: the query, key, value, and output projections. The second sublayer is the feed-forward network, often implemented as a gated MLP, which is the most common choice in recent LLMs. A gated MLP uses three projections: the gate projection, the up projection, and the down projection. The gate projection controls which activation pass through. The up projection expands the hidden dimension, and the down projection reduces it back to the model dimension. Both sublayers are wrapped with normalization layers such as layer norm or RMS norm and residual connection to stabilize training and improve optimization. PEFT updates a small parameter subset or inserts lightweight modules to adapt large pre-trained models. It is because full fine-tuning, which updates full parameters, is often impractical due to the high computational and memory costs. I'll introduce some popular solution of PEFT for LLM. The very popular solution, low-rank adaptation, represents weight updates via low-rank adapters attached to selected projections, which does not update the weight directly. It is compute and memory effective, with competitive performance compared to full fine-tuning. For example, VRAM consumption is reduced from 1.2 terabytes to under 350 gigabytes for GPT-3, 175 billion. While LoRa is effective, full precision fine-tuning is still memory prohibitive, and existing quantization methods fail during training. QLoRA quantizes frozen weights using 4-bit NF quantization for memory savings and enables large model PEFT on a single GPU. With quantization and proposed other optimization techniques, QLoRA achieves full precision performance under 48 gigabyte memory for 65 billion model. Another solution, DoRA, addresses the fact that LoRa has less control over both magnitude and direction components. DoRA reparameterizes weights into magnitude and direction to improve optimization dynamics. It achieves better performance than LoRa, while LoRa itself also achieves competitive performance compared to full fine-tuning. Long LoRa uses shifted sparse attention, S2 attention, and trains embeddings normalization to extend context efficiently during fine-tuning, while leaving inference unchanged. Different from various sparse attention mechanisms, such as strided attention and sliding window attention, S2 attention is effective for PEFT and SFT. Therefore, the benefit is very clear. It enables long context PEFT with lower and practical memory footprint and GPU hours. The figure below explains the efficiency of the solution with respect to model quality, memory footprint, and GPU hours. These solutions focus on the challenge, achieving competitive performance compared to full fine-tuning, while limiting trainable parameters with lower resource consumption. For lower resource consumption, we can note that as previous works used existing methods, we can use another method to further address the challenge. SparseLoRA focuses on lower resource consumption for PEFT by leveraging an existing method, contextual sparsity. So let's consider this question. What if we sparsify the frozen weights to accelerate PEFT? In addition, instead of using static sparsity, we can leverage contextual sparsity, which adapts to the input context. This approach can improve not only speed up, but also overall model performance. In this paper, the authors focus specifically on an output dynamic pruning method, also known as output contextual sparsity method, which determines sparsity based on the current output tokens during training. Contextual sparsity sparsifies the weight at inference time, considering the contextual behaviors of LLMs. The difference from contextual sparsity and static pruning is that it prunes parameters permanently. Therefore, contextual sparsity can capture the importance of parameters depending on the context. Many solutions have been proposed, such as Deja Vu, the first uncovered contextual sparsity, and others such as Katz, Griffin, and Thiel. So, based on contextual sparsity, SparseLoRA comprises three components. First, it uses an SVD-based sparsity estimator to select the active channels neurons for current batch. Second, given this selection, we run the forward and corresponding backward paths on sparsified backbone, reducing computation and activation memory. Third, it updates the LoRa adapters as usual. Let's dive deeper into SparseLoRA step by step. To begin with the first step, neuron selection, we start with the one key question. How should we select neurons? We could select them based on certain metric or a predictor, or simply reuse existing methods. However, previous contextual sparsity approaches only support single token computations. While this is effective for decoding phase in LLM inference, fine-tuning requires multi-token computation. To address this, SparseLoRA introduces a new metric that supports multi-token computation called the oracle. The oracle is a criterion for neuron selection based on intermediate activations. There are two types of oracles. First, feed-forward network value output project activations, and second, QK projections. The first type of oracle, used for feed-forward network and value output projections, starts from the observation that activations generally contain more influential outliers than weights. Because of this, it is effective to use the L2 norm metric computed across the sequence length dimension. We then select neurons according to the target sparsity ratio. The figure on the right illustrates the selection process. Darker cells indicate larger L2 norm values, while brighter cells are pruned based on this metric for gated MLP. We can also observe that the neuron indices are shared within the feed-forward network. Specifically, the pruned raw indices of gate projection and up projection match the pruned column indices of down projection, as you can see in this figure. For the same reason, the value and output projections and the attention block also share their neuron indices. The second type of oracle, used for QK projection, is quite different. This is because QK projection have lower input activation sparsity, making the L2 norm metric less effective. Instead, SparseLoRA uses the QK norm, defined as the element-wise product of the L2 norms of query and key. Empirically, this metric serves as a more reliable oracle for selecting important channels and the QK projections. The figure shows the attention map when the sparsity ratio is set to 50% for the sparse cases. We can see that the attention map produced using the QK norm is more similar to the dense attention map compared to using the L2 norm. Additional analysis under practical fine-tuning settings is provided in the experimental analysis section of the paper. Based off these ideal oracles, we can perform contextual sparsity. We can leverage them while still retaining model quality. However, computing the ideal oracle requires dense computation, which introduces a significant computational overhead. Therefore, instead of using the exact oracle, it is more practical to approximate it. SparseLoRA does this using truncated SVD to approximate the oracle. This approach adds only about 1% runtime overhead and incurs minimal memory usage. This paper then analyzed about various sensitivity. First, layers differs in tolerance to sparsity. This sensitivity analysis shows deeper layers are more redundant and amenable to higher sparsity than earlier ones, as you can see in this figure. So we apply non-uniform ratios over depth. This improves the flops accuracy trade-off at fixed budgets versus uniform sparsity. For token sensitivity, we leverage the observation that fine-tuning batches consist of both context tokens and output tokens used in the loss computation. Output tokens are more sensitive, making them sparse causes accuracy drops, especially in datasets with many outputs, for example, METH10K. This is because output tokens are used in loss computation. SparseLoRA thus keeps output tokens dense and sparsifies mainly context tokens. This preserves quality while still saving compute. For steps sensitivity, we leverage the observation that early training steps are more critical for convergence during fine-tuning. Accordingly, SparseLoRa runs the first 5 to 10% of training steps in dense mode before switching the sparse mode. This warm-up start strategies stabilizes optimization while incurring only a minor cost to the overall speedup. Using SparseLoRa, it shows that it beats various LoRa-based PEFT methods such as QLoRA, DoRA, and LoRa in terms of flops and speedup. On CSR 170K with Llama 2 13 billion, SparseLoRa matches or slightly exceeds LoRa accuracy while requiring only 61 of the flops and delivering 1.3 speedup. Results are consistent across various benchmarks such as BlueQ, PIQA, SIQA, HelaSwag, Winograde, ARC, and OBQA. On Math 10K with Llama 3 8 billion, SparseLoRa reduces training cost by 54% and achieves 1.6 speedup over LoRa with comparable accuracy on GSM-AK, SVAMP, and MAWPS, showing that structured contextual sparsity can cut compute without sacrificing reasoning quality. Under fixed compute budgets, called isoflops comparison on Llama 3 8 billion, SparseLoRa consistently achieves higher accuracy per flop than LoRa on both Math 10K and CSR 170K across 5 to 100% budgets. This indicates practically under production constraints where compute allocation is fixed. SparseLoRa composes with memory saving techniques. With QLoRA on Llama 3 8 billion, SparseLoRa cuts flops to 65% on CSR 170K, up to 1.2 speedup, and 60% on Math 10K, up to 1.3 speedup, while retaining accuracy, thus saving memory and time together. So, to summarize, SparseLoRa brings contextual channel sparsity to PEFT training through a training-free SVD estimator and sensitivity-aware scheduling. It reduces training computation by up to 2.2 and achieving up to 1.6 real speedup, while preserving accuracy on CSR 170K, Math 10K, and other benchmarks such as GLUE, MTBench, and HumanEval. Also, this approach requires sensitivity analysis, which introduces multiple hyperparameters. There is still an opportunity to automatically determine sparsity during fine-tuning or during SFT. Thank you for watching my presentation, and if you have any questions, you can reach me by email at this address.